Okay. Because we will talk about basal eigensystems later in today's lecture, so we go back to our last example on the basal equation. Okay. All right, so consider the basal equation of order nu greater than or equal to 0. Okay, so that, and we write the basal equation, all right, as a Sturm-Liouville equation. Okay. B here, where lambda is a parameter. Okay, and since we have P of x equal to x and Q of x equal to minus nu square divided by x, and R of x equal to x, right? So we know P of x is continuously differentiable, okay, on 0b, on this interval from 0 to b, and R of x is continuous on 0 to b, and the P of x greater than 0, R of x greater than 0 on 0 to b. Okay. Now, although Q of x is continuous, okay, so Q of x is continuous on this half open, half closed interval. It is unbounded near the endpoint x equal to 0. Okay, and also we know that P0 is equal to R0 is equal to 0. Okay, so that's the basal equation. Okay, it's a singular Sturm-Liouville equation. Okay, on the interval I 0 to b. Okay, and So now by the Frobenius method, in our study of ODE, an extended power series, method. Okay, so Frobenius method is a kind of extended power series method, right? The Bessel equation of order nu okay, has a general solution. Okay, YH of x equal to C1 J nu x. All right, so this is a function of x, all right, with parameter lambda. Okay, lambda is all parameter plus C2j minus nu x lambda. Okay, and with j nu x lambda x to the nth power, okay, k from 0 to infinity, and minus lambda k's power here, and 2 to the 2k plus nu's power, and k factorial, and the gamma function of k plus nu plus 1. Okay, and x to the 2k's power. Okay, so this is a power series with even power here. Okay, even power here. Now, and j minus nu, x to the minus nu's power, okay, and k equal to 0 to infinity. Okay, and this is minus lambda k's power 2 to the 2k minus nu. Okay, here is plus nu, right? 2k plus nu for the positive nu here, and here we have minus nu for the minus nu here. Okay, k factorial, and the gamma of k minus nu plus 1. Okay, x to the power. So again, this power series has only even power term here, right? And we have this two. So the j nu and the j minus nu take this form here when nu is not an integer. All right? So when nu is not an integer, okay, we have that. And we know gamma x, okay, is the gamma function. Okay. And this gamma function is defined for all x in R, okay, except at x equal to non-positive integer. So 0 except at 0 or minus 1, minus 2, minus 3, etc. Okay? All right, so this is the H indicator that we know the Bessel equation here is a homogeneous linear equation. All right. So this is a general solution. Okay, general solution. And when nu is positive, it is a non-negative integer, n equal to 0, 1, 2, etc. Then a general solution is here. So we write down YH of x equal to C1. Again, this is J sub n, x, and the lambda, plus C2, and the Yn, of x with parameter lambda. Now Jn takes the same format like this one. So let's say here, where the Jn x with lambda as parameter is the xn's power, and a power series with only even power term. Okay. Now this is 2 k plus n, because now nu is n, k factorial. And this is k plus n factorial. All right, the k plus n factorial actually is equal to, so this number is actually the gamma function when x equal to k plus n plus 1. Okay, so compare with that. When nu is n is a non-negative integer, so gamma of k plus n plus 1, this is equal to the factorial of k plus n. Okay, and the numerator is the k power of minus lambda. Okay, so we have, and y is n, y sub n. The y sub n is more complicated. It's 2 over pi and Jn x lambda times the natural logarithm of x over 2 plus gamma, a constant, okay? I, gamma, let me write it down. Gamma here. Gamma here. Plus the xn's power divided by pi, and this a power series, okay, with even power term, x to the 2k's power, 2 to the 2k plus n, k factorial, and k plus n factorial. And here is lambda k, minus lambda k minus 1, and hk plus hk plus n. Okay? All right, so I will. So this is the harmonic sum will be defined later. So h sub k plus h sub k plus n. Okay. And the third term, there's a certain x to the minus n's power over pi. Okay, and and the polynomial, right? Okay, from 0 to n minus 1, okay, with even power term to k minus n, k factorial, okay, and the n minus k minus 1 factorial. Okay, so you can see the y sub n function is more complicated. Now we have some parameters. First of all, the harmonic sum, so that h0 is defined to be 0, and the h sub n is defined to be the harmonic sum 1 over I. Okay, so this is the harmonic sum, right? Harmonic sum here for all m greater than or equal to 1, and the gamma. So the gamma is the limit, all right, of the harmonic sum minus the natural logarithm of m. Okay, natural logarithm of m here, all right, and this limit exists, all right, and it's called the Euler constant. Okay, so you see here, and now we will. Now you see that they are power series, right? So you can see that the J sub V function is expressed by power series. J sub minus V also expressed as a power series, and J sub n power series, and the Y sub n you call has 3 terms. The third term is a polynomial, so this is well behaved. The second term is a power series, and the first term is also contain a factor of a power series here. So now you have to check the convergence property. Now you can use the root test, right? The infinite power series, okay, in J nu x lambda with nu greater than or equal to 0, okay, all right, so account for this and this one, and also J minus nu and x lambda with nu greater than 0, but not an integer. Okay, so this is this one, the J minus nu function, and the y and x lambda. Okay, right. So which one? This one. Okay. Right. So we have 3 kind of infinite power series. Okay, this one. Okay, this power series. This power series. This is for nu greater than or equal to 0. All right, and here nu is positive but not integer, and the type is here. Okay, in here you can see that we have harmonic sum here. So this is the 3-part series, the even part series. Okay, converge. Okay, converge everywhere. Very interesting. Everywhere in R. Okay, so that their radius of convergence is infinite. Okay. Okay, so the solution, so they have a very good convergence property here. Okay, now, okay, we see that since we know that the Q function minus the nu square divided by x, all right, this function is unbounded. It's unbounded near the endpoint x equals 0, and all right, so we know that, and a solution U of the Basel equation, okay, of order nu maybe okay, maybe unbounded. So maybe unbounded near x, i.e. The limit u go down to 0, x go down to 0, and ux is plus or minus infinity. Okay. So an integral from 0 to b over f of x, d of x, like okay, should be interpreted, right? So interpreted as an improper integral. Okay, like here. So from 0 to b, u of x, d of x is equal to limit epsilon go down to 0, b here, u of x dx here. Okay. Maybe I use f. Okay. For any complex or real valued function f on this open half-course interval such that the integral exists, which means that this limit exists. Okay. Okay, and all right. So the Lagrange. Right. So the Lagrange's identity. Okay. Become. It's here. XLU. Vx dx minus 0 to b x u of x L over v of x. All right, which is limit, and the epsilon goes to so we will write it down as equal to 0. BXLU okay, put into here. Epsilon okay, and as we computed when we show the sub-adjoint, that is in theorem 11.5.8, right? Okay, so that this is, so we have shown, so this is P of x, U prime of x, and V bar of x minus U of x, V prime x bar, and epsilon and B. Okay, and we let epsilon go to 0. Okay, so in here, now since the P of x, the limit epsilon go to 0, P of x, and and P of x is x. So, oh, okay, so that P of E, yeah, okay, because when you substitution x with the epsilon, so this one is limit epsilon go to 0 epsilon, which is 0, okay, so this is go to 0. Okay, so that so you see that this is the limit epsilon go to 0. P B P B U prime B V B bar minus U B V prime B bar. Okay, this product minus P of epsilon. Okay, P of epsilon and P of epsilon and and the U prime epsilon and the V epsilon bar minus U epsilon V prime epsilon bar. Okay, and you can see this term is independent of epsilon, so you can write it down. So this is PB U prime B VB bar minus UB V prime B bar. All right. Okay, and all right, and we see that this is minus P epsilon U prime epsilon V bar minus U epsilon V prime epsilon bar here. Okay. All right. Our purpose is to ask for that that the value becomes to be 0. Okay, so this is our, so that the corresponding stem DLV operator L we will define later. All right, to the basal stem DLV equation. Right, becomes to be self-adjoint. Okay, so we want to impose conditions, all right, on U and V. Okay, so that this is become to 0. Okay, now we look at here. So because as E go down to 0, P of E is 0. Okay, and all right, so what we want is that, so, and this is, so that we will, okay, so we will have, so we will have 0b x LU equal to 0b x U of x right? So we have that, we will have that, which is equivalent to saying that if, so this is our requirement, if we impose the boundary condition that impose that U, V, and U prime, V prime are bounded, okay, are bounded near the endpoint x equal to 0. Okay, so because that as epsilon goes to 0, and we impose that the U function and the U prime function, V function, V prime function, well, they were bounded. Okay, so they are bounded, right? Okay, and so because this is bounded, and this vector goes to 0, so that this limit will, so this one will imply that the limit Okay, it implies that this is 0. Okay, so this is saying that this is 0. And bounded, so we got bounded, okay, bounded near the endpoint. So this implies this one. And satisfy. All right, so these 4 functions and satisfy satisfy that and satisfy the boundary condition and satisfy that that L1 YB plus L2 Y prime B equal to 0. Okay, so this is actually the boundary condition of a regular system theory problem at the endpoint B. Okay, so satisfy this one. Okay, so that this implies that L1 with at least one of L1, L2 non-zero. Okay, and so this implies that because U and V are solutions of the Bessel equations, so that this is UB plus L2 U prime B equal to 0, and L2 VB plus L1 L2 V prime B equal to 0. Okay, and this is a system of 2 linear equations, so that so we have UB U prime B VB V prime B equal to L1, L2, sorry. So this is L1, L2 equal to 0. Okay, and all right, and we can take a bar. Okay, so we can take, say, here, take a bar here. Okay. All right, and that we have said that L1, L2 are reals. Okay, they are real numbers. Right, so both of them okay, right. So when we take the converse conjugate, so here and here, there, right, still satisfy the system 2 linear equations, and we have that. Okay, and okay, and we know that L1, at least one of L1, L2 is non-zero, so we have non-trivial solution, okay, for this homogeneous metric equation. Okay, and so this is implies that the determinant of this coefficient matrix the determinant is 0, right? So which says that U prime B VB minus UB and V prime B bar is equal to 0. Okay, so this difference is 0, which shows this difference is 0. Okay. All right. So this is the boundary condition we imposed. Okay. All right. So this is our purpose because we want to, again, we need the self-adjoint property. Okay. All right. And so we let V sub B, all right, consist of all complex or real valued functions U on this half open half closed interval such that 1, U is continuously differentiable. Okay, on 0B. Second, U prime is absolutely continuous. Okay, on 0B, which implies that the second derivative U double prime of x of U of x exists for almost all x in this interval. Okay, and the third condition is that the second derivative is in L2 space. Okay, and the first condition is that U and U prime, okay, are bounded. Okay, are bounded near the end point x equal to 0, and right, so U and U prime are bounded near the endpoint x equals 0, and in here, right, okay, and here we consider a case that the another boundary condition at another endpoint UB is 0. Okay. All right. So which is the boundary condition UB plus L1 UB plus L2 U prime B equal to 0 with L2 equal to 0. Okay? Okay. When L2 equals to 0, L1 must be non-zero, and so we have UB equal to 0. Okay? So that we just consider this situation. Okay, and so so that you can see in this VB, right, it can be verified again. Okay, it can be verified that V sub B, right, is a vector space. Okay. Okay, so it's a vector space of a vector subspace of the L2 space. Okay. All right. So you see, in this subspace of L2 space, that every member function, right, had satisfied the required boundary constraint. Okay, we were needed. All right, and then the basal Sturm Liouville. So the basal Sturm Liouville operator L, which is from VB to L2. Okay. All right. With it send you to 1 of x and minus x u prime, right? Because r of x is x and the p of x is x here. And the q, so minus is plus nu square divided by x u. Okay, so this linear operator will send member functions in V sub b into a function in the L2 space. Okay, as you can see here. So this is you can see that it involves the second derivative, the first derivative of u, as well as u itself. Okay. And the coefficients of u prime, u double prime are functions of x. Okay. All right. So with this, so this linear operator L, okay, is self-adjoint, i.e., L u v r equal to u L v r. Okay? For all u v in this vector sub v sub b. Okay. So you know that the requirements are needed here. Okay. All right, and so now, okay. Now the function. Now so it thinks j minus nu of x lambda, right, with nu greater than 0. This function you can see here. So this function is unbounded. You see, this function is unbounded as x go to 0 from the right hand side. Why? Because this is the minus nu. Okay, so this is a negative power. Right. So this term will brought up to infinity. Right, as x go to 0 from the right hand side. Okay. So that this is unbounded near x equals 0. And look at the yn. Okay. So when we look at the yn here, and the c here, okay, look at it. It consists of a term that x go to infinity, yeah, as x go to 0, okay. So this one, and a similar behavior is here, right? The natural logarithm goes to minus infinity as x goes to 0 from the right-hand side. Okay, so that it brought up. This is also brought up. Okay, so that this one and not an integer, and y sub n (0, 1, 2) are unbounded near the endpoint x equals 0. Only j nu x and j nu, okay, with nu greater than or equal to 0 is possible. Okay, it's possible. It's possible in V sub b. And then possible to be an eigenfunction, okay, of the basal Sturm-Liouville operator, right, of the Sturm-Liouville operator, right? So that this operator, okay, this operator. Okay, so possible to be the only candidate left is this type of solution, just a nu here for nu greater than or equal to 0. All right. So as we know, that this power series converge, right? For every, so this one, converge this one. Okay. So this power series converge. All right, and all right, and the x nu here. So at the so it has any value. So it defined for every x in the real line. Okay, so that's well behaved. Now, so this is the only candidate. Okay, but remember, for this function, j nu be in VB, okay, then we should check that, of course, j nu is continuous differentiable, and also, of course, that because that it also, you can see that it is infinitely differentiable. So this function is infinitely differentiable, okay? Infinitely differentiable for, so you can take any order of the derivatives. So of course that, and it is quite easy to see that it is absolutely continuous, of course, right? And of course it is in, the second derivative also is in L2 because it's continuous function, okay? Okay, and but we check the fourth point, that the J nu and the derivative of J nu, of course, they are continuous functions, right? So that they must be bounded near the endpoint, of course. So that the only thing we need to check is here, is this condition. Okay? Is this condition. Okay, so operator of order nu, okay, the order nu here, because the parameter nu is here. So this is the basal steam D'Urville operator of order nu. Okay, for a given nu greater than or equal to 0, right? So this implies that. So this also implies that any eigenvalue of the basal Sturm D'Urville operator of order nu must be non-degenerate, which means that if this one is an eigenfunction corresponding to an eigenvalue, then the corresponding eigenvalue must be this one. The J nu must be unique up to constant. Okay, so this is is non-degenerator. All right, now, so we want to know, so when lambda is less than or equal to 0, okay, less than or equal to 0, then J nu x lambda. So we look at that. When lambda is non-positive, okay. Okay, here, if this is non-positive, okay, and so you can see that if this is less than or equal to 0, minus lambda will be greater than or equal to 0. All right, so the coefficient here, every coefficient in this policy must be non-negative. Okay, must be non-negative. Okay, must be non-negative here, and so that especially when k equal to 0 here, we have a constant term, right? A constant term, right? So that this one will greater than 0 for all x greater than 0, and for all nu greater than 0. Okay? Right. So this is always, right? So in particular, that J nu B lambda is not equal to 0. Okay? So this is impossible, right? If we substitute B in there, okay? So this is impossible, all right? So that, right? So that because of this, so that this J nu is not in VB, so that J nu X lambda. All right? So J nu lambda is not in VB. Okay? And then any thus any lambda less than equal to 0 is not an eigenvalue, okay, of the basal Sturm Liouville operator of order nu. Okay. All right. So it's impossible. So if lambda is less than or equal to 0 for any nu greater than or equal to 0, this function, okay, is not in VB, so that it cannot be an eigenfunction. Okay, so lambda less than or equal to 0 is not an eigenvalue. But when lambda is equal to kappa square, okay, so this is positive with kappa greater than 0. Then we have, okay, so we have that J nu X kappa square, right? Because lambda is kappa square, and this is X nu, summation K from 0 to infinity, minus 1 to the K's power, and the kappa to the K's power, to the 2K plus nu K factorial, gamma of K plus nu plus 1, and the X of 2K. And we can, in this case, we can merge the K with X together. Okay, so we can move them together. And so this is what, this is actually kappa nu J nu kappa of X. Okay, and kappa of X with parameter 1 here, right? Because that you can, if you look at here, okay. So this is you can see here. You can see here that 1 over kappa nu, and this is kappa X nu here, right? Summation K from 0 to infinity minus 1 K Okay, and this is 2k plus nu k factorial, and this is gamma k plus nu plus 1, and the kappa x 2 to the k's power. All right, and so you compare this with that. You can see this is just 1 over kappa nu, and j nu kappa x with parameter 1 here, with parameter 1. And this function is defined to be so this function, so this is equal to 1 over kappa nu and j nu kappa x. Okay. Now, the j nu kappa x okay, that where j nu x is defined to be x to the nth power, so that this is defined to be that is j nu x with parameter 1, and which is x to the nth power. Okay, from 0 to infinity, minus 1, I'm sorry, k, to 2k plus nu k factorial, gamma function of k plus nu plus 1, and x to the 2k's power. And this one, where is called the Bessel function of the first kind. So this is the famous Bessel function of the first kind, okay, of order nu greater than or equal to 0. Okay, greater than or equal to 0. And the Bessel function, Bessel functions are types of function, well-studied function. Okay, and it's known that. So it is known that the Bessel function of the first kind, okay, j sub nu, has infinitely many zeros. Okay, so all the zeros, what we call nu 1, alpha nu 2, alpha nu m. Okay, for each nu greater than or equal to 0. Okay, so it has infinitely many zeros, and these zeros goes to infinity. Okay, so we have infinite many zeros there, and this now since the boundary point, the boundary condition at the endpoint x equal to b requires that the j nu and so we require that because this is the, we ask that this function must be in kappa at B, right? So at B, this must be 0, all right? We ask for that. So, okay, if just a new, this function is in VB, okay, so we require that it should be 0 at B. Okay, and so, but we know this is equal to, from here, this is 1 over kappa square J nu kappa B here. Okay, so kappa B must be a 0, okay? Must be a 0. All right? So, so that the lambda nu m, okay, which is just kappa nu m with the kappa nu m to be alpha nu m divided by b. So that we require that this one, this implies that kappa b must be equal to alpha nu m. Okay, must be for some m equal to 1, 2, 3, etc. Okay? Okay. Right, so kappa b must equal to, and the solution, solution for k, so that we define kappa nu m defined to be alpha nu m divided by b. Okay? So which shows that the kappa should be some specific value here. All right. So this is some specific value. And so that the lambda, when lambda is equal to the square of kappa sub nu m, with k kappa sub nu m to be this number, right? In this case, so this lambda is an eigen value, okay, of the basal Sturm Liouville operator of order nu. Of order nu. Okay, so greater than or equal to 0. Which is non-degenerate, as we indicated before, degenerate, right? And has a corresponding eigenfunction. Okay, the eigenfunction we call phi nu m of x equal to the the basal function kappa nu m x. Okay. The m 1, 2, 3, etc. Okay, so you can see we have we have infinitely many eigen values. Okay, we can have infinitely many eigenvalues here. Okay, and as you can see, the eigenvalues go to infinity. Okay, and it has the smallest one. Okay, the smallest one must be just divided by b, right? So the smallest one must be positive. Okay, and go up to infinity. Go up to infinity. All right, and each of the eigenvalue is non-degenerate. So there's one unique eigenfunction, which is just the scale, the Bessel function of the first kind of order nu. Okay, and the scaling factor here for the argument is the kappa nu m, and kappa nu m is here. It's the 0. All right, divided by b. Okay, so you have that. Okay, so we have the situation here. All right, so now for a given order nu greater than or equal to 0, phi nu m, m from 1 to infinity, is an orthogonal eigensystem, because we did not normalize the eigenfunction yet, but they are orthogonal. Okay. Because the Bessel Sturm-Liouville operator is self-adjoint. Okay, so that of the Bessel, all right, Sturm-Liouville operator of order nu. All right. The reason is that since if n not equal to m, the two eigenfunctions, okay, phi nu n and phi nu m, corresponding to distinct eigenvalues lambda nu n and lambda nu m are orthogonal. Okay, orthogonal. Also with respect to the weighting function of x equal to x, okay, i.e. the inner product of these two functions with respect to the weighting function R, okay, is which is equal to must be 0 by the self-adjoint property of the basal Sturm Liouville operator. Of order nu. Right, so which can also be proved as in theorem 11.5.1 there. Okay, and so now with this orthogonal eigensystem, right, we can generate a generalized Fourier series. So for any f in the L2 space, okay, so we consider the space that defined on the finite cross interval here. Okay. The series summation and from 1 to infinity Cn j nu alpha nu n x divided by b, okay, with Cn equal to 1 over the j nu alpha nu n x divided by b, and the square of the norm f j nu alpha nu n x divided by b. Oh, okay. So this is actually 2 divided by b square and the j nu plus 1 square of alpha nu n. Okay. So we know alpha sub nu n is are zeros of j sub nu. But this zeros will not be any zero for the Bessel function of the first kind of order nu plus 1. You can see the order is bigger. Okay, so for bigger order Bessel function of the first kind, this is zeros for the Bessel function of the first kind of order nu becomes to be non-zeros. Okay, so you can see the evaluation. This is a non-zero value. Okay, okay, and here, okay, this one, j nu alpha nu n x divided by b and dx. Okay, so you can do that. Okay, so this is series. This series with coefficient this way. Okay, it's called the Fourier Bessel series. Okay, generated by f. Okay, with respect to the orthogonal eigen system j nu alpha nu n x divided by b for n from 1 to infinity. Okay? And we get this number is because that the square of the norm of this function, okay, okay, so sometimes to indicating the weighting function, we sometimes we index the norm here. Okay, sometimes. Okay, but we know the definition is like here. So this is equal to 0b x j nu, the square of j nu alpha nu n x divided by b dx. And this can be evaluated to be b squared divided by 2 and the j squared by nu plus 1 and the alpha nu n. Okay? So, so this is from the property, okay, of Bell functions. Okay? So they have this one. So now the following theorem right? So the following theorem answer the convergence and representation problem of Fourier-Bessel series, right? So we summarize it in the following. So this is the representation theorem of Fourier-Bessel series. Okay, and so let f be piecewise continuous on 0 to b and have a piecewise continuous derivative on 0b, right? And then first one, the Fourier-Bessel series summation and from 1 to infinity Cn j nu alpha nu n x divided by b generated by f with respect to the orthogonal eigensystem okay, j nu alpha nu n times x divided by b for n from 1 to infinity of the Basel, Sturm, Liouville operator of order new on 0B will converge to the arithmetic average of the left-hand limit and the right-hand limit of f at point x at each point x in the open interval. Okay, so this in the open interval here. And the second, you know, the reason why this is good only for from 0 to b, the reason is here that, for example, at when x equal to b, so this is b here. Now, then the argument is just the 0 of this function. So this is always 0. So the series sum always 0. Okay. So the Fourier Basel function, right? Of course it converges to 0. So it's equal to 0 when x equal to b. Okay. But as you see, the function f may not be 0 at x equal to b, right? Because f just an arbitrary piecewise continuous function and has a piecewise continuous derivative on 0b. Okay, so it may have arbitrary value at the endpoint b here. Okay, right. So that if it happened that f of b is 0, then of course that it will converge to f of b. All right, when x equal to b. Okay, so that is the situation we have, and for 0, okay, it has some specific values, right? So that at x equals 0, we have specific value convergence. So that this is only good for x in between 0 and b. Okay. And if f, all right, if okay, so if f is also continuous, all right, on AC with 0 ACB here, then summation n Cn Jv V and xb. So this Fourier Basel series converge. So converge to f of x uniformly on AC. Okay. And 3, or if f is also continuous. All right, it's also continuous on AB with 0 less than A less than B, and f of B is equal to 0. F B equal to 0. Okay, then this Fourier Basel series converges to f of x uniformly on AB. Okay, and last one. So the last one, or if f is continuous on 0C with B here, then the summation n from 1 to infinity Cn J nu alpha nu n x divided by B converges to f of x uniformly on 0C here. Okay, so that okay. Okay, and so now we will consider the next section about completeness of an eigen system in the L2 space. Okay, so the first we give a definition. All right, a sequence f sub n and 1, 2, etc. of functions in L2 space on AB is said to converge. Okay, is said to converge to a function f in L2 space on AB in square, adder, in square adder on AB with respect to the weighting function R if the distance okay, so this is the square of the distance, which means that we know this is just F minus Fn. So the difference, okay, so we take the norm of the difference, so this is a measure of the distance, okay, so we can say that this is the distance between, so R, okay, so the definition. So this limit just go to 0, okay? So limit go to 0. And so, okay. The square root of the inner product of F minus G with itself is called the distance, the norm of F minus G, and it's sometimes called the distance. The distance between F and G. Okay? So that the okay, so that in square adder, so you can see this is called square adder weighted by the weighting function, right? So this is the square of the adder weighted by the weighting function, and we do the integration. We sum over all possible x by this weighting function, okay? So we call the square adder, and the square adder will goes to 0 as n goes to infinity, okay? Right. Okay. So we define convergence concept called L2 convergence, or which means that a function, a sequence of function L2 converge to a function f in L2. Okay, in square adder. So square adder. So convergence in square adder is defined in this way. Okay. So our interest is that the convergence, for example, that we know the Fourier Bessel series, this one, converge to a function here, pointwise, right? So we have the convergence on the representation theorem pointwise. And so our question is that if we use the partial sum function, okay? So we use the partial sum function there. Now the partial sum function as f sub n, okay? And we want to know that we use partial sum function to construct a sequence of functions in L2. Okay? in L2 there, right? Because that in such a generalized the Fourier series, we know that the eigenfunctions are all in L2. Okay, so the partial sum function must be in L2. Okay, because they are linear combination of functions in L2. So that we have a sequence of functions, and the function we want to know that the sequence of partial sum function converge to this function. You know, this is a function, right? And also it's in L2. We want to know whether it converges to this function, okay, in square adder, okay, in square adder, in this sense, in square. So this is the question we ask ourselves in this section. And before that, we recall we actually we need the following theorem, okay? Okay, the following theorem says that uniform convergence implies convergence in square adder. So if a sequence, okay, f sub n and 1, 2, 3, etc., of functions in L2 maybe, all right, converges to a function f in L2 space uniformly on AB. Okay, uniformly on AB. So that this sequence function converges to this function pointwise, not only pointwise, but also uniformly. Okay, so uniformly. Then this sequence converges to f in square adder. And in square adder with respect to any weighting function. R of x. All right, so this is good for any. Okay, so uniform convergence is a rather strong condition. Okay, a rather strong condition that it implies convergence in square adder with respect to any weighting function. Okay. Okay, and the proof, I have read the lecture notes. Okay, so now we will consider. So now, for an eigensystem, all right, for an eigensystem phi n of say regular or periodic or singular Sturm Liouville problems problem on AB then a natural question. Okay, a natural question is raised up the point. All right. So does the generalized, right? So that's the generalized F Fourier series summation 1 to 1 to infinity Cn phi n generated by a function f in L2 space with respect to this eigensystem, okay, converge to F, all right, to F in square adder on AB. I.e., we ask that the limit, okay, n goes to infinity, and f minus the partial sum, and R2 is 0, where the partial sum function okay, so we ask this big question. Okay. In previous sections, we answered the convergence equation either pointwise or uniformly, right? But this time we ask convergence in square adder. Okay, convergence in square adder. All right. So we know that the generalized Fourier series okay generated by F okay is all right the Cn, so the Cn actually is equal to okay, it's equal to this one. Okay, and so this is equal to okay. So we have that. Things, as we can see that okay, so we actually so that the coefficient actually is calculated by forming the inner product of the generating function f with the nth eigen functions phi n divided by, this is just the square of the norm of phi n. Okay, as we know. So, okay, so this is the coefficient is defined this way. Okay, so we define the generalized Fourier series in this way. Okay. Now, and so that, okay, and as we so now we consider approximation to a function f in L2. Okay, consider by an arbitrary linear combination of the first n eigenfunctions phi 1, phi 2, up to phi n. So we consider approximate f by such a function dn phi nx, where d1, d2 up to d sub n are constant in C. Okay. Right. So we want to approximate as in section number 4. In section number 4, we study the approximation to a square integrable function by an arbitrary linear combination of sinusoidal functions, okay, of sinusoidal functions, and here we consider the general case, okay. All right, so so that we can compute that the square error the square adder. Okay, the square adder of this n term approximation by t sub n of x, x here is En f minus t sub n square with back to the weighting functions, and so that this is becomes to so we can to here f r minus summation Cn square Yn square r plus summation n from 1 to n dn minus Cn square phi n r square. Okay. Okay, where Cn is the coefficient we define here. Okay, the coefficients in the generalized Fourier series generated by f. Okay, so we can end up with this expression, right? Now with this expression, and we get this one with a procedure similar to the procedure we have went through in section number 4. Okay, and from here you can see there is a lower bound. Okay, so you can see the first two terms are independent of d sub n, or independent of Tn. So this is Cn square. Okay, so this is, and the equality, holds if and only if dn equal to Cn, i.e. If Tn of x is equal to the partial sum function of this generalized Fourier series. Okay, so we know this result. Okay, so that's, we have f minus xn, the subpartial sum function. So the the square adder, all right, the square adder of the approximation by the partial sum function is equal to, of course, this is minus okay, and then we know that the square adder by the approximation by arbitrary function t sub n, it's equal to minus plus square, so that this is our bound All right, so now we can summarize the results in theorem 11.6.b. Now for any n greater than or equal to 1, the best approximation, okay, the best approximation in square error, so measured by square error with respect to a weighting function of x to a function f in the L2 space, okay, by an arbitrary, by Tn with d1, d2 up to dn arbitrary constant in C is that Tn of x is equal to the partial sum function okay, and the minimum square error we denote as En tilde. It's just the square of the norm of f minus summation and from 1 to capital N, Cn square and phi n r square. Okay. All right. All right. So from this best approximation, theorem, okay. So from the previous theorem, okay. So so let's suppose that there is a series Dn phi n. Okay, so there is a series converge to f in square error. All right. So suppose we have this situation square error with respect to a weighting function of x on AB i.e. that the limit as n goes to infinity f minus Tn. Okay, so this is the square error. The square error goes to 0. Okay, square goes to 0. Then suppose we have that. this situation with so we have that. Now, by theorem, 11.6.b, okay, that so we have that we have f minus partial sum. This is equal to this then f minus dn partial sum, right? Because this is always less than this one, and so when we take the limit, also less than the limit, and this is 0, and this is 0, okay? Right, so by sandwich theorem, this implies that the limit okay? So we see that from here, we know, and we have that, and limit square as n goes to infinity. So this is always equal to 0. All right? So we know, okay, and dn must be equal to cn for all n. All right, so now we can write down the previous result into the next section. So if a series dn by n converges in square adder to a function f in L2 space with respect to a weighting function of x, then, so if we have that, then dn must be equal to cn for all n greater than 1, i.e., this is series must be the generalized Fourier series generated by f. Okay. So if we have such a series and converge in mean square to a function f, then this series must be the generalized Fourier series generated by f. Okay. So this is the only possible choice. The only possible choice there. All right, now Now, so that if such a series exists, if such a series converges to a function f in square adder exists, then this series must be this series. Okay, so this is the only candidate. All right, so the next question is so under which condition that this generalized Fourier series indeed converge to f, right? To f in square adder. Okay, and before that we see things that we know that this is equal to by our computation before. Okay, so we know that the distance, the square of the distance between f and the partial sum function, the partial sum function, okay, is here, is this distance. So that the limit n goes to 0 of this distance. Okay. It's 0 if only if the limit n goes to infinity. Sorry, infinity. Okay. F square minus summation. Oh, square. Sorry. Okay, so this one goes to 0, and so if only if f r square, right, is equal to the limit n goes to infinity, which is just the series sum. Okay, sorry. Okay, right. So we know that, and this shows that the partial sum function converges to f in square adder, right? So that this happened if and only if that the square of the norm of f is equal to this series sum. Okay, and in section 4, this is called the possibles identity. Okay, so this is called the possibles identity. So we have the possible identity if and only if the generalized Fourier series generated by a function f converge to this f in square adder. Okay, in square adder. Now, and so a very interesting question is that it is possible that the possible identity always true for any f or any function in the L2 space. Okay, in the L2 space, and in this case, it will mean that the eigensystem phi n is very spatial. Okay, so we give us definition. So an orthogonal set. Okay, all right, phi n from 1 to infinity. So an orthogonal set of functions in L2, AB, an orthogonal set. And we know that any eigensystems of a regular or periodic or singular Sturm-Liouville operators on AB is also an orthogonal set. Okay, because the corresponding the corresponding Sturm-Liouville operators is self-adjoint. So we have that. So an orthogonal set of function in L2 space, right? So each phi n is in L2 space with respect to a weighting function of x is said to complete. Is said to complete in L2 space if for every function in L2 space, okay, the generalized Fourier series summation okay, so the generalized Fourier series generated by f, okay, i.e. Cn is defined by here okay, set of so I have to say of non-zero. Okay. An orthogonal set of functions with all right, so with non-zero norm, all right, so that would be better because that by definition this is the square of the norm of phi n, all right. All right, so I think we need this requirement. Okay. So the generalized Fourier series, okay, converge to f in square adder. Okay, with respect to the weighting function. Okay, R of x. All right. So that if the possible identity is true, okay, for any function f in L2 space, then this orthogonal set phi n, okay, is called complete. Okay, it's called complete. Okay, so now it is clear that an orthogonal set phi n in L2 is complete in L2 space with respect to a weighting function of x, if only if the possible identity holds for every function f in L2 space. Okay. So now we can state a theorem in the textbook. So if an orthogonal set phi n in L2 with is complete. Right, it's complete in L2 space with respect to a weighting function of x. Right, so if we have that, then any function f in the L2 space, okay, which is orthogonal to every phi n with respect to the weighting function of x, right, must be 0. Okay, for almost all x in AB. i.e. almost all the norm, the square norm, is 0. Okay? And if, in addition, f is continuous on AB, then f must be identical to 0 for all x in AB. So this is the zero function, exactly, if f is continuous. Okay. All right, and the proof, please see the lecture notes. Okay. Okay, so now in the previous sections we studied eigensystems of a regular over periodic over singular stem-Liouville problems. All right. So and we know that such an eigensystem is an orthogonal set. It's an orthogonal set. Okay. So the question is that do these eigensystems complete? Are these eigensystems complete? Okay, so so the question is here. X an eigensystem of is an eigensystem of regular periodic over singular stem-Liouville problem on ABE complete in L2 space. All right, so this is a big question. Okay, and so the answer is yes. Okay. So the answer. So I was just say yes for, all right, for regular and periodic stem-Liouville problems. On AB, okay, so for regular and periodic stem-Liouville problem on AB, as well as for Legendre and basal stem labia problems. Mass 1 and 0B respectively. Okay, so the answer is that for any regular stem labia problem, the corresponding eigensystem is complete in L2. And also for a periodic stem labia problem on AB, all right, the corresponding eigensystem is also complete, right? And for the two singular stem labia problem we studied, which are the Legendre stem labia problem on mass 1 to 1, and the basal stem labia problems on 0 to B, right? Then their corresponding eigensystems are also complete in L2 space. Okay, so that they're so nice that we have this one, and I give proof for this result. Okay, so please read lecture notes. On section, the lecture notes for section 11.6. Okay. Okay. So I will not go to the details of the derivation for this general answers here. Okay, but I ask you to read through the lecture notes. Okay. Okay. So I stop here, and so next Tuesday is a holiday, so next Monday is still in the holidays, and we will not have any quiz. Okay, and of course we will have no recitation class. Okay, all right. So I'll see you next Thursday.